I'm very pleased to welcome Umesh Vazirani. Umesh is the Roger A. Strauch Professor of Electrical Engineering and Computer Science at the University of California, Berkeley, and a co-director of the Berkeley Quantum Computation Center. Umesh has been a pioneer in the field of quantum computing with several significant and impactful works for about 3 decades now. He has contributed to many other fields in theoretical computer science as well, example, randomized and approximation algorithms. He was awarded the Fulkerson Prize for 2012 for his work on improving the approximation ratio for graph separators and related problems. He's a fellow of the ACM and a member of the National Academy of Sciences. Umesh will talk today on the recent quantum supremacy experiment by Google, which came quite a bit in the news recently, and various theoretical considerations behind it. So over to you, Umesh.
Thanks, Rahul, and really nice to see to travel to Singapore so in such an easy way. I've been the way I see it is we are now all isolated vertices sitting on a complete graph. So it makes things harder in some ways, but much easier in some other ways. Okay, so let's see.
Okay, so let me again just remind the audience. So Umesh is happy to take questions in between the talk as well. If you may please write your questions in the chat window, then we can take them up. Or if you you even want to just unmute your mic and ask the question, you can do that as well. Okay, is that that's correct, Umesh, right?
Yeah, that's good. Yeah.
Okay.
More interactive, the better. Okay. So so what I want to do is talk about some of the ideas and the events behind this recent Google Supremacy event, experiment, which I'm sure you've seen a lot of coverage about it. Now, you can start by asking what was this, what was the, how big an event was it really, and what were the ingredients that went into it? And I think that for people in the know, there's no doubt at all that it was a very significant step in terms of quantum hardware. So what Google managed to do, which was so exciting from the viewpoint of experimental quantum computing, was they managed to implement quantum circuits on 52 qubits for a depth of roughly 20. 52 qubits acting for roughly 20 steps. And the most important part was with gate fidelity of about 0.99. Right, so this was a major achievement. Now, on the other hand, there's something one should say, that if this is all they had achieved, if they had achieved this kind of level of quantum hardware, there'd have been several hundred, maybe several thousand people around the world who would have been extremely interested in it. But it would not have created the kind of universal a kind of splash that it did. So what it took to create this splash was the combination of this, this real big leap forward in terms of the hardware, plus these theoretical schemes for achieving quantum supremacy. So it was, if you look at it, what really made this such a interesting event was this. Was this major experiment combined with the assertion that they were achieving quantum supremacy, and that took a lot of work. So I want to tell you a little bit about what that means and how that was achieved. Okay, so what's quantum supremacy? So quantum supremacy is something that we in computer science can relate to at a very fundamental level, because it's in our bones. It's at the basis of computer science. So it's just an experimental violation of the extended Church-Turing thesis. So the extended Church-Turing thesis, lies at the foundations of computer science. It says any reasonable model of computation can be simulated on the simplest one, probabilistic Turing machine, efficiently, in polynomial time. And sort of you could replace Turing machine with cellular automaton, and what I have on the screen here is the game of life, invented by John Conway. Now, starting with some of the earliest days of quantum computing, the reason that we were so excited about quantum computing, the reason that quantum computing became such an important thing for us in computer science and in general, was the realization that quantum computers violate the extended Church-Turing thesis. So this goes back into the early history of quantum computing. And in fact, to show that quantum computers violate the extended Church-Turing thesis, we had to do three things. We had to show quantum computers are programmable, that they are digital, meaning they are actually robust to errors. And initially, in this initial period, we just showed that they were digital, robust to 1 in poly-n errors in each of the gates. And that they could produce super polynomial speedups on some computational problems. Now, the computational problems that they provided speedups for were not useful in any way. They were just challenge problems. They were completely useless. But then over the next few years, these themes were explored in very beautiful ways. So starting, of course, with Peter Shor's work, which showed actually that you could get exponential speedups for practical problems. There was work on quantum fault tolerance, which showed that quantum computers are robust not only with respect to 1 in poly-n noise, but even with respect to constant errors on the gates. And then with respect to programmability in simpler and simpler models, with simple universal gate sets and this Solovay-Kataev theorem. So there was a number of things that made this all much more robust. Now, there was one other aspect of this that was very interesting, which is somewhat philosophical, which is something that lies at the foundations of quantum mechanics. So in quantum mechanics, when you have a quantum state of n qubits, these n qubits, to describe them, it takes an exponential number of amount of information. You need 2 to the n complex numbers to describe the state of these n qubits. But on the other hand, if you try to extract information out of them, you can get at most n classical bits of information about the state. This is a fundamental theorem called Holevo's theorem. So if we were to just blur our eyes a little bit, then to a first approximation, even though the state takes 2 to the n complex numbers to describe, we can essentially, the state to a first approximation acts like a black box, and it doesn't allow us to know that there's 2 to the n amount of information sitting in there. And so one of the things that was realized early in in these very early days of quantum computing was that the fact that quantum computers violate the extended Church-Turing thesis allows us to probe this Hilbert space in which the quantum state sits in a way that one might have thought that the axioms of quantum mechanics don't allow us to do, that they forbid us from doing. And so, for example, this is something that we wrote in our paper back then. For example, one might naively argue that it's impossible to experimentally verify the exponentially large size of Hilbert space. However, an experiment demonstrating the exponential speed up offered by quantum computation over classical computation would establish that something like the exponentially large Hilbert space must exist. Okay, so now, I said that quantum supremacy is an experimental violation of oops, sorry, I was missing. Okay, quantum supremacy is an experimental violation of the extended sharing thesis. And how do we achieve it? Well, one way to achieve it, if you could, is just to use Shor's factoring algorithm as a basis, right? You create a challenge problem, choose two large primes P and Q, multiply to get n times n equal to P times Q, ask the quantum computer to factor n, and if it succeeds, then quantum supremacy has been achieved. But the problem is the reason that that's not how we want to approach quantum supremacy is because we have no idea, implementing factoring is very hard on a quantum computer. And so there's this quote from Aronson and Arkhipov, which I think is very nice. It sort of gets to the heart of the problem. What they said in their paper on quantum supremacy is that proving a quantum system's computational power by having it factor integers is a bit like proving a dolphin's intelligence by teaching it to solve arithmetic problems. Basically their point was we should have quantum computers do what they're really good at doing rather than what we want them to do classically. And in fact, they started a long sequence of theoretical works on quantum supremacy with their paper on boson sampling, and then similarly on IQP by Brebner, Josa, and Shepard. And the interesting thing about Google's experiment is that it deviated from these works in the sense that instead of choosing these works where there was some theoretical basis for quantum supremacy, they sort of started at the other end and they said, what can we actually implement? And so once they started asking what can we implement, then this left a gap, which is would what they implement actually achieve quantum supremacy? And this took a bit of doing, as I'll talk about. So what did Google actually do? So what they did was they implemented, this, circuit with superconducting qubits. There were 52 qubits, which are denoted by the X's here. And they had coupling between these qubits, which were the gates. Okay, so this was a way to probe a 2 to the 52 dimensional Hilbert space. And the experiment relied on this Goldilocks principle. So what's this Goldilocks principle? Well, 52 is a number that's large enough so that 2 to the n is very impressive. But it's small enough that one can do that corresponding computation on a classical supercomputer. For 52 or for, by simplifying it somewhat, and, but in some way one can do a computation that's of that order of magnitude. Okay, so what's the particular experiment they did? Well, what they did was they initialized each of their qubits to 0. Okay? That at the beginning of each experiment. Now, what was an experiment? So the experiment was they once and for all picked a random quantum circuit C and fixed it. So what's a random quantum circuit? Well, it was a way to create, some quantum gate between adjacent pairs of qubits. So maybe the right, the diagonals pointing to the right first, and then in the next step, the diagonals pointing to the left. So you pair up the qubits in some way, and then you subject them to some gates according to this fixed random quantum circuit C. So this quantum circuit C has 20 layers in it. So you do these 20 layers of quantum circuit, and at the end of that, you measure all the 52 qubits, and you get a random 52-bit string. Let's call it X. So X is now sampled according to the output distribution of this quantum circuit C on input all zeros. Okay. So now, what they're going to do, what they did in this experiment is they fixed C, and they ran this experiment over and over and over again, each time collecting a random 52-bit string X. Now, what they did was they used the supercomputer to compute what's the probability that the quantum circuit C should actually output X on input 0 to then? And they did this for every 52-bit string X that was output. And then they checked whether the sampled X's are actually consistent with the output distribution of the circuit. So they wanted to solve the problem to say, look, is it plausible, is it likely that these output strings X actually came from the output distribution of this quantum circuit C? So how did they do this? Okay, so let's look at, if we say we have a particular string X and we say, what's the probability with which the circuit C would have output X? Well, and let's figure out what should the expected value of this probability be. So if the circuit C actually outputs a uniformly random n-bit string, then whatever string X it output should have been output with probability 1/2 to the n. So the expected value of the probability with which it was output would be 1/2 to the n. If, on the other hand, the circuit C was deterministic, on input 0 to the n, it only output one particular string X. So then if you look at the output X and you ask, with what probability should it have been output? What's the expected value of the probability with which it was output? It would be 1, right? Because no matter, you would always see the string X and it had probability 1 of being output. So in general, there's this property that whatever the probability distribution is, the circuit will tend to output the strings which are more likely rather than less likely. So the expected value of the probability of the string being output in general would be higher than 1/2 to the n, but probably not as high as 1, because that's the probability, that would be the expected value if the distribution was a delta function. Okay, so now what's the case when you take a random quantum circuit and you look at the output? Well, then the expected value, expected probability, if you take a typical output and you ask, what was its probability? That expected probability would be 2/2 to the n, twice as much as in the case of the uniform distribution. Okay, so in this experiment, what they did was they took these samples X1, X2, and so on. They estimated the probability with which this should have been output for each of them, okay, and took the average value of that. And when they did this over millions of trials, their estimate was something like 1.002 divided by 2 to the n. Okay, so remember, what they were expecting to see was 2. They saw 1.002. And then what was it Google was saying about this? Well, they were saying, look, we did millions of experiments. We repeated this millions of times, so much that we are pretty confident that this was larger than 1. 1 is where it would have been, 1/2 to the n, right? 1/2 to the n is where it would have been if it was uniformly random. And they were saying, well, this is not uniformly random. We think it's the quantum circuit. Okay? So as you can see, this leaves a lot to be explained. How do we know? So there are two questions. How do we know that random quantum circuit sampling is hard for classical computers? And how do we know whether the Google machine actually succeeded in sampling from the output of the chosen random quantum circuit? So at the moment, if this is all you saw, you would be thinking to yourself, this is not very good evidence at all that they actually implemented the particular quantum circuit that they claim to have implemented. And so this is where theory comes in. This is where the theory comes in. Okay, so there are actually 3 kinds of evidence that one can cite, and I'll present them not in chronological order, but in the order of the most formal to the least formal. Okay? The the property is going to be that the most formal evidence is, is going to show something that's general, but it's not really going to apply very closely to this 1.002. And the least formal evidence is going to apply completely directly to this 1.002, but it's not going to be as convincing. So, so there's this trade-off. Okay, so the first kind of evidence looks, it relies on the following property, that probability distributions generated by quantum circuits look very different from those generated by classical circuits. Okay. So because the probability that a quantum circuit outputs X can be, it's given by the constructive and destructive interference across exponentially many computational paths. And so the probability can be written as a difference, a difference of two quantities whole squared. If you can think of it simplified as the difference of two real numbers squared. Now, in complexity theoretic terms, this has a real consequence, because you see, usually when you have a classical probabilistic circuit, if you ask what's the probability with which it outputs a particular value, that sort of sits in the class sharp P. It's a counting problem. And if you look at the approximate version of it, it sits in the polynomial hierarchy. For a quantum circuit, the probability that the circuit outputs a particular element is the difference of two positive real numbers. So it's in this complexity class gap P. And so it's hard even to approximate this probability. So this gives us a distinction between quantum and classical. In the classical case, approximating these probabilities should sit inside the polynomial hierarchy, whereas in the quantum case, it should be outside of the polynomial hierarchy. And so, if you sort of work this through with the machinery of complexity theory and worst case to average case reductions, you get some theorem which, I've stated very informally. This is not really, you have to look more closely at what it says, but essentially, morally what it says is, if a polynomial time classical circuit can output from the distribution very close to the output distribution of a random quantum circuit, then the polynomial hierarchy would collapse. Okay. So this seems really great, except that, of course, there's a very big caveat. Here, close means very, very close. So, in terms of the number that we saw before, which was 1.002, this would apply if it was 1.99999, not 1.0002. Okay, so now we should go on to a different kind of evidence, and this kind of evidence is this so-called heavy output generation property, right? So this was first there was an initial paper on this by Aronson Chen, and then more recently by Aronson and Gunn. Gunn is now, he was an undergrad with Scott Aronson when he did this, and he's now a grad student in Berkeley. So, and this more recent paper actually ties a certain hypothesis to the actual the actual test that the Google experiment is doing. Okay, so what's heavy output generation? So, it sort of starts with this idea that a quantum circuit usually will generate heavy outputs. If it'll more likely generate an output X, which has high probability, rather than an output X, which has low probability, right? But then they sort of posited a hypothesis. You could think of it as a complexity hypothesis. And well, you could say it's a bit ad hoc, but it's sort of, you should think of this in the spirit of the exponential time hypothesis or something, so it's sort of saying, look, let's assume something pretty strong. What we're going to assume, and the reason to assume this is that we don't yet know how to show that this hypothesis is false. So it says that there's no efficient classical algorithm which, when it sees one of these outputs X, that it can guess with probability even slightly less, more than half, whether this output X has above median probability or below median probability, right? So in other words, what you do is sort the strings X according to the probability with which the circuit outputs them. And now you ask, does this particular output X fit in the lower half or in the upper half of all the strings? And of course, you can guess with probability half just by flipping a coin. And this says you cannot even guess with probability half plus 1 over 2 to the n by any efficient classical algorithm. And what they were able to show is that if you assume this hypothesis, then actually the Google experiment would succeed. Okay, there's a little bit of a quibble here, which is, well, if you wanted the Google experiment to succeed, then you'd have to replace, this half plus exponential in minus n to half plus exponential in sort of m. Where m is the number of gates, not the number of qubits. If you really insist on showing exactly what we want to show, then you have to do a back of the envelope calculation. Sorry, it shows me that the internet connection is a little bit unstable, so I just want to make sure that you can still hear me.
Yes, Umesh, yes, yeah, we can hear you, I can hear you.
Okay, great. And while I'm stopping here, any questions?
Okay, so there is one question by Kishore Bharati. He was asking, is it obvious that we should get 2 over 2 to the n for random quantum circuit?
No, it's not. It's actually a calculation. So basically, if you look at the output of a random quantum circuit, it turns out that output distribution looks Poisson. Okay, it's a Poisson distribution with a certain mean and variance, and so then if you figure out what's the expected value of P of X, it turns out to be 2 over 2 to the n. It's just a fact, right? Physicists call that distribution the Porter-Thomas distribution. So if you hear physics talk, that's what you'll hear, but it's really just a Poisson distribution.
Okay. Yeah. So are there any other questions that people would like to ask since we're pausing for now? Okay, maybe not. Maybe we can proceed.
Okay, so the other way we can proceed is just by doing a back of the envelope calculation, right? So we can say, well, look, the error rate was 1 over 100, right? The fidelity was 0.99. The number of gates was roughly 1,000 because it's 50 qubits, 20 depths, so 1,000 gates. So what's the probability that there's no error, right? That's 1 minus 1 over 100 is the probability that there's no error in one gate. The probability that there's no error at all in all 1,000 gates is 1 minus 1 over 100 raised to the power of 1,000, which is roughly, if you approximate, it's like 2 to the minus 10, which is roughly 1 in 1,000, right? So which is roughly how much of a signal was being seen in the Google experiment, right? And so the hypothesis, the hypothesis that they put forth in the paper was, well, the output distribution behaves like a convex combination of the ideal distribution of the random quantum circuit and the uniform distribution, right? So now by collecting enough samples, if you run this enough times, 1,000,000 times roughly, you should be able to be fairly sure that you're seeing some signal from the quantum circuit. Okay, so as you can see, you probably want to have some convex combinations of these sorts of arguments to sort of build up some kind of confidence in this claim. And actually, there's a lot of ongoing work right now on trying to get these claims, to get more confidence in these claims. And some of that work actually is quite interesting, but it's not been written up yet by various authors, so I won't refer to it yet, but it's all in the works. Okay, so I think it should be clear by that there are two things you should take away from this. One is that this was a real experiment. There was a lot of blood and sweat that went into the experimental aspects of it. But it also took a lot of doing to actually justify the fact that supremacy was achieved. And in fact, it wasn't a fully convincing kind of justification, but it was enough to say, this was a good first experiment in the line. And this is an important aspect of quantum supremacy. It's not a one and done experiment. It's actually something that's going to be done over and over again with increasing confidence in the assertions. It's a little bit like for those who know about it, the Bell experiment, right? About entanglement, which has been done over and over and over again over the decades. Now, I should say that this is also a very important scientific experiment, in the following sense. That in physics, one of the important things is testing the limits of the theory, like in the limit of high energy or in Planck scale, very small size, very large velocities. And now, there's a new limit in which to test physics, namely quantum mechanics, which is, that this exponential growth of the Hilbert space and the exponential computing power and the exponential complexity, this is a very counterintuitive aspect of the theory. And so this provides a new limit in which to test physics, that of high complexity. Okay, so if we sort of say, well, this is an important experiment that must be performed in the future many times, and it has to be refined over time to eliminate loopholes, that exist in the experiment. One of the key aspects that has to be dealt with is better guarantees on the, that the underlying computational problem is hard for classical computers, as well as guarantees that we are actually verifying the quantum device is actually solving the problem that it's claiming to. And so let me say, in the rest of the talk, I'll describe a little bit more about how one would go about doing that, more generally. So maybe I'll stop here for a couple of more questions, or see if there are any questions, and then proceed. And in the meantime, let me. Okay, I just want to see how I'm doing on time. Okay.
Okay, so do we have any questions now?
I have a question.
Yes, please.
So Umesh, when you say verification, currently you mentioned that it takes a lot of time.
Yes.
So you expect this to be polynomial, or do you think exponential time verification would also be okay?
Actually, that's what I was going to get to next.
Okay.
So that's a great
Okay.
question. So you're really setting up the rest of the talk. I'm not sure how much time I have for the rest of the talk. I should ask, but that's what I was planning to cover.
All right, thanks.
I think Umesh, since we started, I think maybe 11:10. I think we can go on till maybe 20 more minutes. Is that correct, Yvonne?
You can, I think.
Yes. So Umesh, probably 20 more minutes. Yeah.
Okay, great. So So let me, okay. So actually what I want to talk about next is in fact, how do we do this kind of supremacy without, when we go beyond this Goldilocks limit? So in the Goldilocks limit, what we were saying was, let's assume that the verifier can spend exponential time by using a supercomputer and is small enough. But now we are assuming that's no longer the case. So now the problem is that the quantum computer is, well, it's both a black box and it's also very powerful. So our classical verifier is very weak by comparison. And so what would be nice is if we could somehow constrain the quantum computer, you know, a lot, but then we don't want to also constrain it in a way that it loses its power, right? Because after all, we want to verify that we really implemented a quantum computer. So this seems somehow contradictory. So here's an idea. So the quantum computers aren't all powerful, right? So there's such a thing as post-quantum cryptography. So there are classical crypto systems that even quantum computers cannot break, right? This is something that's, you know, there's a big push to implement this and to deploy this. There's a NIST challenge to replace the current cryptography with post-quantum cryptography, which will be secure even if they are quantum, you know, even when quantum computers become available. Okay, so what it provides is cryptography that even a classical computer can encrypt, and it can even decrypt with a secret key. But without the secret key, even a quantum computer won't be able to decrypt the message, right? And so what we are going to try to do is use post-quantum crypto to level the playing field between the classical verifier and the quantum computer. Okay? So there's a right way and a wrong way to do this, right? The wrong way was what I referred to earlier. So what we could do is we could cripple the quantum computer by forcing it to play on the classical verifier stuff. You know, that's not going to be good. The right way is we want the quantum computer to play on this turf where the verifier has an advantage, but where the quantum computer can still do everything that the quantum computer can do, right? So we don't want to cripple it. We want it to have its full power, and yet have it play on turf where there are certain things that the classical verifier can just do better. And so this is something that you know, that we did with Zvika Brakersky, Paul Cristiano, who was and Urmila Mahadev, and Thomas Vidic. So the last three were my former PhD students. Zvika actually visited Berkeley at some point. Okay, so what we can do is use post-quantum crypto to make sure that the quantum computer holds a qubit, which is in a special form. Okay, it's a superposition of 0 and 1. So it's a single qubit. It's like either 1 over square root to 0 plus 1 over square root to 1, or 1 over square root to 0 minus 1 over square root to 1. So these two states are usually referred to as the plus state and the minus state, respectively. Okay, but even though the quantum computer has picked one of these two states, it actually doesn't know which one it's holding. And in fact, what it knows is an encryption of the bit B using this post-quantum cryptography. Okay, and now what the quantum computer can do is, in fact, it can also give this encryption of B to the verifier, and the verifier has the secret key and would know exactly which of the two states it is, whether it's a plus state or the minus state. Whereas from the quantum computer's viewpoint, it's a completely random state. It has no knowledge about it whatsoever. And the way this is implemented is using what are called trapdoor claw-free permutations. Okay? It's a function which is 2 to 1. So you know, as you can see there in that figure, and it has a property that the function f is easy to compute. It's very hard to find a claw. It's very hard to find a collision like this. You know, two inputs that map to the same output, right? x0 and x1 such that f of x0 equal to f of x1. But of course, if you have knowledge of the trapdoor, then you can invert. So you can pick a y, you can invert it to get x0 and x1. Okay, so and there's an implementation of trapdoor claw-free functions based on LWE, which is one of the prime candidates for post-quantum cryptography. Okay, so now using this, you can create this protocol for efficient verification, scalable verification of quantumness, or supremacy. And it looks like this. So, conceptually what you do is you first tell the quantum computer, you fix F, right? You fix your, trapdoor function F. Then what the computer does is it gives you back a Y. Okay, you give it a challenge 0 or 1. If you give it a challenge 0, then you ask the computer to give you back one of the pre-images of Y, either x0 or x1, and it does so. And if you give it 1, then you challenge it to give you some other value depending on x0 and x1. We call that D. It has now this protocol has a property that a quantum computer can answer either challenge of your choice. So you give it a challenge either 0 or 1. There's a way that it can go through this protocol and answer all challenges. There's no polynomial time algorithm, either classical or quantum, that can answer both challenges. So in other words, once you get to this point, once Y has been committed to, after that, you cannot answer both challenges. If you do, then you've broken the quantum cryptography and post-quantum cryptography. And then we know that even quantum computers can't do this. So now, how do we show that even though quantum computers can answer whichever of the two challenges you're asking for, how do we show that a classical computer couldn't possibly answer both queries? So the answer is, this has something very important to do with the fact that quantum computers, while they are working, you really cannot measure them. As soon as you measure them, you collapse the state, right? So you can't, whereas a classical computer, as it's working, you could keep track of everything that's happened so far. After it gave you the output, after it sent you Y, you could keep track of the state of that computer, and then first give it the challenge 0, see what it answers. Then you rewind it to that same state it was in, and give it the challenge 1 and see what it answers. So since that's inherent to classical computers, that you can rewind them. So if a classical computer guarantees you that it'll answer whichever challenge you want, then it actually has to be capable of answering both challenges, which means it's capable of breaking the cryptography. Okay, so I'm going to slightly skip, depending on how much time, maybe I can. Okay, so how do you do this? Well, okay, so what the quantum computer can do is it can go into a superposition over all x, compute f of x, and measure f of x. Once it measures f of x, it gets a random y, which it reports to the verifier. And now, its superposition on all x will collapse down into the superposition over only the x's which are consistent with the output y, which means it's going to be in a superposition of the two pre-images. Now, if it gets a challenge 0, then it just measures this in the standard basis. And so it'll send back either x0 or x1, which the verifier can verify. If it actually gets the challenge 1, then what it does is it measures this in the Hadamard basis. And in the Hadamard basis, when it measures it in the Fourier basis, then it measures some n-bit string D, and D has the guarantee that it's a random n-bit string, which has the property that it's inner product with x0 plus x1, where x0 plus x1 means bitwise addition mod 2, that D dot x0 plus x1 is 0. So it has it gives you an equation on x0 plus x1. So, this is exactly what you do in Simon's algorithm. Okay, so, and then what one can do is actually show that, for this LWE based claw-free functions, they have an adaptive hardcore bit, meaning the knowledge of the pre-image of any pre-image x0 or x1, and any D, right? Together with a better than 50-50 guess for D dot x0 plus x1. If you can do this, then this implies an efficient algorithm to find a flaw. Okay, so okay. So actually, if you think about this, this same protocol a little bit more, then beyond quantum supremacy, verifiable quantum supremacy, you can actually use it to do certifiable quantum random number generation, which means, what you end up getting is, through following this protocol, you would end up with when you follow this protocol, you actually end up showing that this protocol generates random bits, that the quantum computer, which you are verifying is quantum, but beyond that, you're also verifying that the output is truly random. It's not random in a pseudo-random sense, but it's statistically random. Okay, this is something that there have been a number of protocols for over the years, for how to get random numbers from two non-communicating quantum computers, where you don't trust the quantum computers and you want to test and claim based on the test that you've done that the output is truly random. Of course, this is something that in a classical world, you cannot possibly, expect. It's so clearly counterintuitive that even Dilbert, knows about that. And then once you have these primitives, actually you can use it to do many other very remarkable things. So two of these, which were done by Urmila Mahadev, were fully quantum fully homomorphic encryption, which is where you have a quantum computer in the cloud, and you want to delegate a quantum computation to it while maintaining the privacy of your data. How do you do that? Well, this was completely, it was completely unknown how to do it, how a classical client could do that before Urmila's work. And the other is verification of quantum computation. So again, in that same situation, you want to verify that the quantum computer honestly computed, output according to some quantum computation. So so there are if you're interested in this, there are two very nice popular level articles on this. Popular level, which actually explains some of the inner workings. So these are very well written articles in Quanta magazine, which if you haven't been looking at Quanta magazine, you should, because these are very well written articles that explain some fairly interesting advanced sort of papers. Okay, so let me. I think I'm pretty close to having used up my time. So let me try to have some discussion. So so the first thing is, Google's quantum supremacy experiment. I'm sure if you really followed what the media had to say about it, there were actual criticisms from IBM about whether they actually, how big an achievement it was and so on. I think, those of us who saw these criticisms, I think it's pretty much, it's pretty clear that those were not so well founded. I think the experiment was really quite, it was quite an achievement in terms of the experiment itself. It also required major insights from complexity theory to justify, right? It was not at all clear that quantum supremacy had been achieved. And, I would say even now, we have some confidence in it, but not that much, right? But it was a very good first experiment. It was enough to sort of say, here's a first, there's a reasonable chance that quantum supremacy might have been achieved, right? In the same way that when you saw the very first experiments on the Bell experiments, right, on the Bell inequalities, where the first experiments actually were not the ASPE experiments, but there were some experiments done at UC Berkeley, which even predated that. And so, okay, but so I think it's fair to say that there are major gaps in the theoretical justification that supremacy has been achieved. And I think this experiment is going to be repeated many, many times in the future. And there's a lot of work yet to be done to create these future experiments. I should say that the verifiable supremacy result that I spoke about, there are actually improvements to that have been done. There's some recent work that we've been doing which shows how to actually implement it in a more general way, using with fewer constraints on the cryptographic primitives that you're required to use for it. And with those, then these experiments become more practical. And that's the hope so maybe what I should say is that, in fact, there's another way to look at this particular experiment. I think it actually established a blueprint about how these future experiments will happen in quantum computing, at least some of the most interesting ones. So the ones that are going to break these barriers, the barriers are going to be both experimental as well as computational. And this is true no matter whether you're talking about quantum supremacy or error correction, or how do you know, how do you do benchmarking? How do you know that the quantum computer is doing what it's doing? For all these kinds of questions, there's going to be a computational element and a complexity theoretic element, and there's going to be an experimental element. And this quantum supremacy experiment was one which involved a close collaboration between the people working on these theoretical aspects and the experimental aspects. And I think that's a blueprint we'll see over and over again. And so I think that there's in the period that's coming up, we'll see a lot more questions of a computational nature, which are going to have this kind of an impact. Okay, so there's one other thing I want to say here, which is that quantum supremacy, or this experimental violation of the extended Church-Turing thesis, it provides a completely new way of probing Hilbert space, right? So the fact that you have exponential power, that there's exponential computing power, gives you a constraint on Hilbert space, which is not captured by just the information theoretic properties alone. And if you look at the axioms of quantum mechanics, you might think that there are ways in which you really cannot probe the Hilbert space. And so, all the results that I've been talking about show that you can probe the Hilbert space in ways that you would think that it's completely impossible to probe, either through computational complexity or through the use of cryptography. And I think that this is an interesting new paradigm, which we've been exploiting from the computational viewpoint. But I think that there's probably room to exploit it, to think about it also from a physics viewpoint. What would it mean to probe Hilbert space in these completely novel ways from a physics viewpoint? So, that's an open-ended question, which I think is worth thinking about and exploring, and seeing whether we can really formulate it well, or how to really make progress on it. Okay, I think I'll stop there.
Okay, so let's thank Umesh for a great talk. And yes, so now we can take questions.
Maybe I'll stop the share so I can at least see who is in the audience. And then I'll share again if need be. So it would really help me if people were to actually start their video so I can get some sense of who is in the audience.
Okay, so we have a question.
Nice to have a bit of a conversation.
Right. Umesh, so these people are putting their questions on the chat window. I wonder whether you're able to see the chat window. But anyway, I'll read it out as well.
Maybe could the people involved actually ask the question? Or?
Oh yeah, maybe you can just unmute your mic and ask the question. David, you wanted to ask the question, right?
Yes, hello. Thank you for the nice talk. I'm not an expert at all in this domain, but my question is the following. So, the fact that the quantum computer output statistic is 1 over n power n, rather than 1 over 2 power n, rather than 2 over 2 power n. Does it mean that quantum superposition somehow is not surviving during computing, and then the quantum computer behave more like a classical random generator or something like that?
Oh, I see. So you're asking the fact that in the experiment, the statistic was very close to 1 over 2 to the n. It was 1.002 as opposed to, which was very close to 1. You're saying, does this mean that it was almost, classical? Is that the question?
Yeah, something like yes.
Okay, so I think that I think that no. So what it means is, I think the way you should think about it is, or the hope is that what that means is that there was a small amount of quantumness that seeped through. And so actually Scott Aronson has a proposal for quantum random, verifiable, quantum random generation based on this experiment, based on Google's experiment. So he has an even more elaborate assumption, like the one that I showed you, that he had formulated. And under that assumption, if you collect enough enough samples from the output of this quantum circuit, and then you do the tests and it passes, then there must be some actual min entropy in the output, true entropy in the output. And so you can actually collect those outputs and then use classical randomness extraction techniques to get uniformly random bits from.
Okay, thank you.
Okay, Junie, please, can you unmute your mic and ask the question?
Yeah, sure. Can you hear me?
Yes.
Great. Thanks for the talk. I'm a little curious. I'm not sure if I fully understand what you mean when you sort of say exploring the Hilbert space in a way that the axioms of quantum mechanics don't.
Well, no. Yeah, so, I did not mean that, okay, so what I was saying was not that the axioms of quantum mechanics do not allow, because obviously they do allow it. But what I meant is, if you do a naive reading of the axioms of quantum mechanics, and you say, well, from the axioms of quantum mechanics, it seems like, you have your state, quantum state, it takes 2 to the n complex numbers to describe it. But as soon as you measure, when you measure it, you look at the consequences of those axioms, and you get Hollevo's theorem, which says you cannot get more than n bits of information out about what's going on in there, right? So now, which means that, naively you may have thought, and this was what we were struck by in the early days of quantum computing, that naively you may have thought that nature is covering her tracks, and that what's going on behind, behind the scenes, behind the veil, maybe nature is working really hard behind this veil. But when you look at what's happening, everything looks like it's very simple, right? And what I was trying to say is that, look, in fact, and that you might not, we might never be able to, from the axioms of quantum mechanics, it's completely consistent. It might seem consistent that we'd never be able to know that behind the scenes there's an exponentially large Hilbert space, right? That that nature is covering her tracks perfectly. But in fact, what we're saying is, once you establish that there's a violation of the extended Church-Turing thesis, right? And you say, look, we were able to implement a quantum computer that solved a problem in n steps, which should have taken 2 to the n steps classically. Right? In only in a very small amount of time, which should have taken more than the age of the universe classically. Then we can say, look, because the time was short, the length of the computation was short, the width must have been very large. So there must have been an exponential width to the computation. So we'd have shown that something like an exponentially large Hilbert space exists, because we showed that, there's an exponential width to the computation. So that's the sense which I meant that you can show properties of the Hilbert space which you would have thought are impossible to show. And then I was saying in a computational sense, we can also reach in and talk about, well, there are, we can even verify things about the quantum state behind, you might have thought that there's no way to verify what's actually going on inside the quantum state because it's too big and too hard to verify. But in fact, we can reach in through these cryptographic ways. And so to me, this seems to be opening up a door a little bit towards reaching into Hilbert space in ways that we might naively have thought were forbidden to us. And so, what I'm sort of hoping for is that physicists will start thinking about these ways of reaching in to see if there's something, more, from a more physics viewpoint that they can think of that you can do that maybe I'm not thinking about because I'm thinking more from a computational viewpoint.
I guess it seems to me, if you just wanted to prove that the Hilbert space is exponentially large, meaning to say it's not simply just a state of having product, right? It seems to me just the existence of entangled states really show that you have an exponentially large Hilbert space.
Not really, because you can have a Bell state or a cat state, but it doesn't show an exponentially large Hilbert space.
It doesn't prove that it's exponentially large. Yes, that I agree. Proof that it's exponentially large, I think, requires a little bit of thinking, but it certainly shows, right, that you wouldn't have states that are just simply product states. So it doesn't scale in the way that you would think it scales if everything was unentangled, essentially. So I think you can show that the scaling is different in some sense by the very fact that you have entangled state. But then I would think, I'm not sure if you wanted to prove exactly that it's exponential might be a little tricky. But at least that's the way I'm thinking about it.
Hi, Umesh. I always get a bit wary when I hear about the exponential sized Hilbert space, because there's also the exponentially sized probability simplex, right, for randomized
Of course, yes.
algorithms. So how can you distinguish the effects of the two?
Well, this is that's a very, very good point, and that's where that's why one has to look at it in more subtle ways, right? That's where the fact that the probability of outputs sits in sharp P versus gap P. This is an important distinction. Where approximating those probabilities lies in the polynomial hierarchy versus in it might be hard for the hierarchy. That's a big distinction. So in fact, it's true that you can look at it at this level, but then you probe a little further, and these differences become more subtle, and that's what makes it more interesting, of course.
Yes.
Yes. Any more questions?
I have a question.
Yes, Kishore. Yes.
Yeah. So a very nice talk. I mean, the bound 1 by 2 to the power n. If I can think, more from the quantum foundation like perspective, it's like some kind of classical bound, and 2 to the power 2, like 2 by 2 to the power n. That's more like some kind of quantum bound. And you were, creating this parallel between like Bell non-locality, like the experiment which happened by Allen later, where they showed violation of Bell inequality, and then this quantum supremacy experiment. So I was thinking, do you think like some kind of inequalities which work in the local setup, not in the non-local setup, seems like similar to Bell inequality, would that be useful to, probe the non-classicality?
Sorry, I'm not sure. I'm not sure I followed. So are you taking the analogy with the Bell inequality and running with it? So you're
yeah. So what I'm saying
on that path.
Yeah. So Bell inequality is more like it works in a setup where you are like you have like separated non-communicating devices, and you want to prove the presence of entanglement or something. Yeah. So I'm thinking in a setup where like you have a single device and you are trying to like prove whether it's doing something quantum or
no, that's so I think you're getting at some. Let me try to see if this is what you mean.
Yeah.
So there's a certain way in which cryptography, post-quantum cryptography, is taking the place of two entangled but separated devices here, right? That in fact maybe you can use quantum this post-quantum cryptography to actually break up the quantum device into pieces that that for all practical purposes somehow are separated from each other in a space-like way. Maybe that's possibly that's what's happening underlying these results, and that's what's going on, right? And that's the that's the feeling that we get at various stages with some of this work, that there's that we are actually setting things up so that if you think of the quantum computer as being adversarially controlled, then pieces of it sort of are out of control of the they cannot be centrally controlled in one. This is a bit vague, but that's what that's a flavor one seems to be getting.
Okay, so like I would like to add more to this, like if I can. So like so like there is this analog of Bell inequalities for like which works for the single party setting also, this thing called non-contextuality inequality. Mm-hmm. And I have been like partially exploring this and written a few papers along this direction, like how to do self-testing, for example, in the single party setup and all. And yeah, I mean, do you like maybe I can like send you my research at some point, and like would like to see whether like more like taking the quantum foundation kind of perspective and trying to show like something cannot be achieved based on physical principles. Yeah.
Right.
Yeah.
Great. Yeah, sure.
So Umesh, I had one question.
Mhm.
So, like in terms of showing a violation of extended Turing thesis, right? Like broadly speaking, okay. So first thing that unconditional violations are still I mean we still don't know of a venue where we can potentially show unconditional violation, right?
Well, we'd have to, what you mean is that if we were to show an unconditional violation, we'd resolve long-standing open questions in complexity theory.
Yes, right. So one is to base on a very strong computational, well-established computational assumptions like pH collapsing and so on, right? I mean, for example, like even factoring, even if we did have a quantum computer which could factor, I mean, it's because we don't I mean, it's not an unconditional violation, right? Or for factoring,
We don't have any unconditional violation, unconditional results in complexity theory, right? Almost none. Yeah, almost no unconditional results in complexity.
Yes, correct. But I'm saying that, like formally, if you want to violate extended Turing thesis, we have to show super polynomial. I mean, the original thesis is about the super polynomial unconditional.
Right. So since we don't have any super polynomial lower bounds in complexity theory unconditionally, so it's
So we've still sort of not too close to unconditional violations. And now in terms of conditional violations, right? Let's say even like pH collapsing and so on. It is a you mentioned that there's still some theoretical issues. So maybe they're related to the error being like constant. We have to do it for constant error, these samplings and so on, right?
Right. Yeah, these are not easy issues actually to deal with.
And currently and then with constant error, there's also this issue of classical verification, because once there's a constant noise, then even classical verification becomes not super easy and so on and so forth, right?
Well, so there are different issues here. So one, if we could do, if we could show that that the problem is hard, that the classical problem is hard with with constant error or something like that, right? So with some constant variation distance, that would be a big step forward, but it wouldn't deal with the verification problem, right? And then
yes.
for the verification problem, then you would have to actually prove something closer to this this heavy output generation hypothesis that Scott had, right? Which is more like an exponential time thesis, right? Exponential time hypothesis kind of thing. It's a very strong assumption, but then even that's not sufficient. So you have to go exponential in M, and then you're skirting very close to the the upper bound that you get by Feynman path integral, right? So if you do the Feynman path algorithm, then you get some algorithm, and then this is just backing off, saying even somewhat better than that is already hard. So it's a we don't know of a better algorithm, but it's assuming quite a lot, right?
Right. So
just understanding this that terrain, I think is very interesting, and I think there are some some interesting papers in those directions as well.
Right. So to sum up, I mean, the current Google supremacy experiments, sort of gave us, practically speaking, strong evidences, right? Even for conditional separations, But to formally establish condition, like, you know, a conditional separation, let's say basing on pH collapsing, that is yet to take place. And now, do we have, do we foresee that, you know, let's say, because, you know, recently there was some news that potentially, you know, maybe IBM was claiming that they might be having 1,000 qubit computer by 2023 or something like that, right? So even assuming we have such a thing,
I think it's
huh?
it's sort of you know, these future
Yeah, the future things, yeah. So
little,
so they had some roadmap to it or whatever. So even assuming that we have such a thing, let's say a few years from now, do we see a venue where we'll be able to establish, right? Establish, say, conditional separation?
well, I think that that, you know, at that point we may be able to do this scalable verification, you know, using post-quantum crypto.
Right. Okay.
And that would be much more well formed, right? It would have a much more.
But again, LWE is not based on pH collapsing, right? Or LWE is just again our belief, right?
Is a great assumption, right? It's
it's
somebody assures you that either quantum supremacy has been achieved or LWE has collapsed. That's
correct. But again, I'm saying the LW, we are not yet able to base LWE on, not some very strong things like pH collapsing, right? It's more like factoring we think is hard, but we are not able to base it on, something more established like pH collapsing or anything.
Well, I think
it's something that we don't have. I mean, people are trying hard. We don't have an algorithm, but we're still not able to base it on more accepted complexity theoretic assumptions.
Well, but if you are going to take that line, then wouldn't you say that pH collapse is just based on the fact that we haven't made it collapse yet?
No, I agree. But I'm saying that, okay, let's think of something as sacrosanct. Let's take pH as collapsing as sacrosanct. Then we still need to relate it to that sacrosanct assumption, right? I mean, because, of course, I mean, even factoring, we don't expect, right, a polynomial algorithm, but except that we are not able to yet relate to a sacrosanct assumption.
Yeah, so that might be, that's a fair point. Although somebody else could say, well, that's sacrosanct from your viewpoint. They would regard LW as more sacrosanct.
Already sacrosanct. Okay, sure.
Yeah.
So even factoring, some people will be willing to regard it as sacrosanct, maybe. I don't know. Okay. Any other questions?
Can I ask a short question?
Yes.
You don't mind? So we know basically that for the sampling from a random circuit is a difficult problem if you don't assume any noise. So what happens, assume when you start assume there's like noise in a circuit, so you have instead a noisy circuit. How do we know that it's still like hard to sample from? Like, is there some guarantee or proof that if there's now a certain amount of noise present in the system, is it still like hard to sample from, or is it like a threshold at some point basically where you go from it's easy to sample to hard to sample?
Right. So that's So that's what I was trying to get at with these three levels of formality, right? So, in the complexity theoretic version of it, when the first pH kind of polynomial hierarchy kind of version of it, we could tolerate very little noise. Then there was the the Aronson-Chen work where they had this much more concrete assumption about telling whether an element is heavy or not, and the assumption said that you cannot tell the difference even with slightly better chance than 50%. And if you assume that, then you get noise resilience, a lot of noise resilience, right? So So, but you're getting that noise resilience in exchange for assuming that you cannot, you cannot tell whether an element is heavy or not, whether it's above median or below median, except with exponentially small probability.
Okay. I know that that you can sample like from noisy 1D circuit as long as you assume the gate fidelity is below a certain threshold. So if the gates are noisy enough, you can basically show that you can efficiently classically simulate from one-dimensional circuits.
Right.
So I was wondering, like, does it mean there's some kind of threshold in the noise resilience, or?
Yeah. So I don't know. That's a yeah. So I'm not sure what happens with this. How much one has to push the assumptions to make it work. That's a good question.
Thanks.
Any other just last few questions?
Can I shoot a quick one? Hey, Umesh.
Yes.
Hi, Anurag.
How are
You're
you?
everywhere.
Sorry?
You're everywhere. You're in Singapore as well.
Yeah, as you said, it's a connected graph now. So yeah. So thanks for the very nice talk. One quick question. In your verification scheme, right? There are 2 rounds of interaction with the computer.
Yeah.
It's a very nice result. But I just noticed that the Google's verification scheme, it wasn't so good, but it had like just 1 round of interaction.
Yeah.
That was like, that's it. And just they verify. So do you think it's possible to get to 1 round?
Yeah. So, I think, okay, I always, I think we have a 1 round result, but, I haven't thought about it for a little while. That's why I'm a little bit, but I think so. I think that there's a 1 round there.
Nice.
But I'm not, I'll have to think about it a little bit.
No, of course. Yeah.
Maybe when you're more local, we can talk about it.
Yeah, exactly. Very soon. Yeah.
So in case we don't have any more questions, let's thank Umesh again, and maybe let's do that with our mics unmuted so that we can all clap. Or even these symbol claps also are good. Okay, Umesh, so thanks for very nice talk, and
great to see you guys.
Yes.